Шановні колеги, шановні учасники школи, для нас велике задоволення представити наступного доповідача. Сергій Фролов з університету Піттсбурга співпрацює з Харковом, з харківськими науково-дослідними інститутами, підтримує активно харків'ян всі ті часи з початку збройної агресії Російської Федерації і всіляко є завжди локомотивом з того, щоб посилювати співпрацю між Сполученими Штатами Америки та Україною. Тож сьогодні він покаже, як квантові точки можуть бути застосовані як квантові технології для технологій, сучасних технологій та розвитку подальших квантових матеріалів. Сергію, як нас чути? Вітаємо, добрий ранок.
Вітаю, Андрію, дякую. Чутно, вас чутно, мені чутно?
Так, чудово. Тож передаємо мікрофон.
Ага, дякую. Я не знав, чи будуть школяри присутні. Тобто в мене багато такого матеріалу базового початку. І ще, що я хочу казати, що якщо у вас є питання, то, будь ласка, українською я гарно розумію, але, на жаль, викладати фізику я не можу українською. Тобто, якщо ви мені дозволите, то я буду англійською викладати. І слайди у мене англійською також.
Так, жодних проблем. Всі розуміють. Так, англійською чудово. Є школярі, тож вони з зацікавленістю хитають.
Школяри speak English? Окей, добре.
Yes, of course.
Yes, good. Okay, no, today я switch to English, okay? So, I will talk about quantum dots, and quantum dots are small objects where quantum mechanics starts to play a role, and you can find discussion of quantum dots in different contexts. For example, chemists synthesize very small clusters of hard matter, and they call those quantum dots. They mostly study them by means of optics. They may be similar to these type of blobs on the surface of a material, but they can be even smaller. And that's not what I'm going to be talking about, because I am an experimental physicist, and I have a research laboratory here at the University of Pittsburgh where we measure electronic transport, which means we send electrical current through devices, small nanoscale objects, and we measure voltages. Or if it's a superconductor, then there is zero voltage. So I will be talking about quantum dots in this quantum transport context. And I will also explain how they are used for creating qubits, quantum bits, and of course, perhaps paradoxically, what we can find in quantum dots is charges, but it is advantageous. It's better to define qubits using spins of those charges, spins of electrons trapped in quantum dots. What I also want to say is that our time today is not very long, although you're probably already tired from several days of this stuff. High quality intensity material. But if you wanted to know more, I took this material from my bigger courses on quantum transport and solid state physics, and you can find those videos on YouTube. So while I was talking, you're probably looking at these pictures, and you can see that there is a different scale that quantum dots can reach, from nanometers to microns and even more. although this particular one, this is a carbon nanotube. It is a micron long, but it is very, very narrow. It is just a few nanometers wide. So the total volume of this object is pretty small. And some of these are single molecules, and some of these are electrical circuits that are defined by very complicated electrodes. So this is maybe the closest to what I work on, and also this one here. So before we dive into quantum mechanics, I think everyone would agree that when we are talking about a very small metallic object that can hold charges, we have to discuss electrostatics. Why is that? Because the smaller the object, the smaller is the capacitance of this object. So for instance, here's a formula, basic formula for capacitance, well, in this case, electric field, but here's a capacitance of a sphere. And in general, capacitance is proportional to the size of the objects, and I guess linearly proportional to the size of the object. So if we're talking about nanometers, we all agree it has very small capacitance. But what that means is that the energy that an electron has, if you manage to stick it onto this very, very small sphere, can be very large, because the charging energy has capacitance in the denominator. So you put a charge of one electron on a very small sphere, you actually have to spend a relatively large electrostatic energy on this operation. And here at the bottom is a table where you can see for different characteristic sizes of these objects, what kind of capacitance you will have, and then what kind of electrostatic energy this would require in the units of Kelvin, in the units of degrees Kelvin. And so you can see here that already if it's a few microns, micrometers, so not even in the nano regime, we are getting to about 1 degree Kelvin. 1 degree Kelvin in energy units is 86 micro electron volts. 86 micro electron volts. So it's electric charge. This electrostatic energy of that would correspond to 1 Kelvin. So it's kBT, Boltzmann constant times temperature, converted to electron volts, will be 86 micro electron volts for 1 Kelvin. And in my lab, we have dilution refrigerators, which go to 10 millikelvin. So we are way below this energy scale, even for large objects like this. And so we will have a regime where thermal energy, excitation over some kind of energy gap, will be smaller than the energy of 1 electron in a 10 micron volume. And 10 micron, if you haven't experienced it, human hair is 100 microns, so this is a tenth of a human hair. So this is small, but it's not that small. It's already a human size. And of course, if you go down to nanometers, you can see that you climb up in Kelvin and you go into 10 Kelvin, 100 Kelvin, and even above room temperature, which is 300 Kelvin. So a very, very small sphere, you will see electrostatic effects up to very high energies. And what that means is that you may not have enough energy to put the charge you want on the quantum dot. And so if you think about it, what it means is, suppose you're trying to pass a current through this object. So we build a circuit with a source electrode and a drain electrode. So we connect it into a circuit with a battery. Let's not talk about the gate for now. And we're trying to pass a current through this circuit. And what that means is that electrons hop onto the quantum dot and they hop off of the quantum dot. In fact, This is what's required to see any of these interesting effects, because if we connect the quantum dot very tightly with very low resistances to source and drain, then charges can actually move freely, or you can think of it as adding a very, very large capacitance to this small object, and then charging energy becomes small again because the total capacitance becomes very large. But if we separate the quantum dot with large resistors, or even put tunnel junctions where electrons have to actually quantum mechanically transition from source onto quantum dot and then off the quantum dot, then you have to think about really individual electrons hopping on and off the dot. And then while they're trying to get on the dot, you have to ask the question, do they have enough energy to be on this quantum dot? And so one way that to get energy we already discussed is from thermal excitation. So just get energy from the randomness of motion of electrons at a certain temperature. And you might not have enough of that energy. And then the other way to get energy is to raise the potential in the source so that they have enough energy to actually fall down onto the quantum dot. So that's what we do by connecting it to a larger battery or to a controllable voltage source. And then, yes, we can also get energy from just supplying electrostatic energy through another battery that is capacitively coupled. So this battery is not in the circuit, not in the path of current, but it creates electric fields on this small sphere and adds capacitive energy. Okay, so now my slides are, yeah, so we already talked about electrostatics a little bit. We'll come back to it. And now the quantum part. You know what this equation is here, right? Schrodinger's equation. So this is the quantum part, because also when you have a very small object, then the individual particles on that island, such as electrons, in a metal, their wave functions, so they're quantum mechanical statistical functions that describe them and that we describe here as psi. Their size, their wavelength of the wave function could also be characteristically the size of the quantum dot itself. This could be comparable. And so then what happens is the energy levels of electrons in this dot become quantized. And this is one of the basic problems in quantum mechanics that you learn when you start studying quantum mechanics, which I did in third year of university. We solve this equation, this differential equation of the second order, to solve for this function, and for V, for the potential energy. This is kind of like kinetic energy, and it's like potential energy. We put some kind of trap. In this case, a square well potential, a well that is the shape of a square with infinite tall walls. So there is nothing outside, and there is sort of infinite energy to be outside and zero energy to be inside. And it's a one-dimensional potential square well. So if you substitute this function into the equation, and you can solve for psi and also for the set of e's, which are the coefficients, just the numbers that are solutions of this equation. And they actually happen to be the energies of the levels in this particle in the box problem. So here it's already solved. And on the screen, you see both the wave functions. So the first one has no nodes. The second one has one node. And then the number of nodes keeps increasing. And always you have the wave function be zero at the ends of this potential, the potential well. And that's because outside energy is infinite. So there is a zero chance for the particle to be outside. Now, if the energy was not infinite, then there would also be little tails of the wave function sticking outside. And in free space, if we solve it without any confinement, then this wave function would be like a propagating wave, like a photon. It will just be a traveling wave. But in a confined structure, they're standing waves, right? And so they form these patterns like standing waves in a water, on the surface of water. Okay, so this is just to bring everyone on the same page about this. And perhaps also interesting that if it's a square well, infinite potential, then the energy separation between energy levels grows as we go up in number. If the solution number 1, number 2, number 3, the E values keep running away. If we put in a parabola, a parabolic potential, or it's called harmonic oscillator, the solutions are actually equidistant, which is very interesting and is used a lot in quantum computing as well. But to make qubits, we need the energy levels to be at different distances. And that's because we want to have a unique energy spacing, because we can come in with that photon of that energy difference and control just between the two states of the qubit, the up and the down, or 0 and 1. And here in this kind of ladder, we will not know where we are in our space of solutions, because we can apply this photon and propagate ourselves up. And if they absorb another photon, it would go to a third level and a fourth level and run out of our space, computational space, right? So this kind of
May I have
potential
a
is,
question?
yeah.
So for real quantum dots, how good the approximation of infinite walls? Does it work well, or there are some limitations for upper energies?
Yeah, so depends on what experiment we're running. So if we want to send any current through the device, right? So let me transition to the next slide, perhaps. So any kind of measurement like this, sorry for pixelated graphs, but here we measure G, which is derivative of current, conductance, differential conductance. But think of it as current. If we want to get this signal, we need to pass electrons from source onto the quantum dot, off the quantum dot and into the drain. And from the quantum mechanics point of view, it means that the wave functions have to overlap and the potentials cannot be infinite. But for qubits, that is perhaps not a very good situation, because that means all of the stuff, all of the electrons in the leads, in the source and the drain, are also coupled to the wave function of the important electrons that carry quantum information in the middle. And so at least during the operation of the quantum processor, we need to decouple those leads. And so we need to raise the barriers. And so we have ways of dynamically doing that by applying extra gate potentials to make the barriers very high and effectively cut all overlap of wave functions. But that doesn't mean there is nothing under barrier at all, right? There could be some, what's this called, evanescent tails, right? Little tails that decay very, very fast underneath the barrier. Okay, so this is an experimental paper from a few years ago, 20 years ago, but it's a very nice paper, very illustrative and educational, because here, these quantum dots, they were grown by a very elaborate process of molecular beam epitaxy in these pillars, which are called nanowires. So nanowires these are about 100 nanometers in diameter, and they're made of a material called indium arsenide. It is a semiconductor, so it's a conducting material. But where you see the dark streaks here and here, they switched to a different material, and they switched from indium arsenide to indium phosphide. So they replaced an arsenic atom with a phosphorus atom, and they kept indium flowing. And what that created is two potential barriers. So the dark regions, potential for electrons to be there is much higher because the band gap of this semiconductor is higher. I can't explain in the limited time what the band gap is, but imagine like I drew the one-dimensional potential to solve the Schrodinger equation. In the dark region, it's very high, and in the light regions, it's very low. And these experimentalists from Sweden, they were able to also control the distance at which these barriers live. So here, they're separated by a larger distance, few hundred nanometers, and here they're separated by a small distance. So, of course, in a smaller quantum dot, which is here, what we are enhancing is, well, both the charging effects, but also the quantum effects, because the wavelength of electrons inside this indium arsenide becomes comparable to the size of the quantum dot. So we go from this very regular pattern of high current and low current, high current, low current, which just happens due to charging energy. I will explain in the next slide why it happens, to this very irregular pattern where the different distances between peaks directly tell you what the quantum energies are, the confinement or orbital energies are of electrons in this small quantum dot. Now, just the fact that current goes very low, almost to zero, and then high, and then low again, and then high, is also very interesting, right? Because this is not something you would see in a piece of metal, like in a laboratory that you run an experiment, maybe at the university. You send current through any object, you will not see it turning on and off like this. And this is a manifestation of discretely adding individual charges to this very small island. So this is a manifestation of charging effects. Remember, I told you that there could be a situation where you don't have enough energy to add another electron to the quantum dot because it's so small and charging energy is too large. Well, in these regimes where the current is low, this is what happens. You don't have enough energy to put an electron on, and current blocks. Current is stopped like at a red light. And this is called the Coulomb blockade. So the basics of it are described by these equations. They are not extremely elaborate. But basically, again, we can recognize the structure here as a charging energy, charge squared divided by capacitance. But now this charge is a complicated function because there is the sort of the charge which is a variable, n, number of electrons on the island. So at every moment of time, there is n electrons on the island. N could be 0, but n could be 1, 2, 3, and so on. So there is n electrons on the island, but then we also have to subtract the electrostatic potential that is contributed by the gate. So there is another voltage that puts electric field on this island, which makes it either easier for electrons to go on the island if it's a negative, if it's a positive potential that attracts electrons to the island, or if we apply a negative potential, it pushes electrons off the island. And this is described by this parameter Vg, which is externally controlled by an experimentalist. And now this sum over n is the sum of all the quantum energies. Right? So in a large quantum dot, there will be a regime where maybe the charging energy is still significant, but the quantum energies we can neglect. They are very small. But in a small quantum dot, we have to consider both the charging contribution and the quantum contribution, right? So whenever it is above temperature, we will be able to resolve it. And our temperature is 10 millikelvin, which, if you remember, I told you 1 Kelvin is, let's say, about 100 microvolts. That means 10 millikelvin is what? 100 times less. So it's 1 microvolt, something like this. So anything that is 1 microvolt and above, we can resolve an experiment. And microvolt is a very small voltage. Okay, so then we can calculate something that is called either addition energy, or a more technical term is the electrochemical potential, which means how much energy do we need in comparison to all the energy that's already present in the system let's say there is n-1 electrons in the system already, how much extra energy do we need to add another electron and go from n-1 to n? So this energy difference is important because that's what we need to supply for each electron by the source drain potential or by the gate for current to flow again. And so this is what we actually looking at is the energy difference, not the absolute value of energy. And so for that function, we just subtract un from un minus 1, and so we get this expression here, which is proportional to n to the first power. And then there is a term related to capacitances and, of course, a quantum energy. So if the lower energy level is already occupied, we may not be able to go into it because electrons are fermions. I don't know if this requires more discussion, but basically what you have to remember is that each quantum level, you can put one electron, and then the next electron has to go to the next quantum level. The only exception is if the electrons have opposite spin. Then you can put the first one and the second one on the same level. And this is called the Pauli exclusion principle. So this is something fundamental to quantum mechanics. And what's interesting is in quantum dots, you can sort of observe it directly, that it works, that you can only put one electron per quantum level. Okay, so now this is how we usually think in my field about transport through these kind of quantum dots. We visualize it with the source chemical potential, drain chemical potential, and the discrete chemical potentials on the quantum dot. So source and drain are assumed to be very large, and that means there is a very, very high density of quantum levels there, and basically becomes continuous, right? But there is the upper level here, and there is an upper level here. So all the states below are occupied, and all the states above are empty. And this is how you can understand Coulomb blockade, why current would stop. So suppose you have a chemical potential in the source right here. And that means that you can contribute electrons of any of these energies to the quantum dot up to this level. We have all of these electrons available. Now, here on the quantum dot, we have the n-1 level below the source level. So one of the electrons here can actually tunnel, hop across this black thick barrier, and hop onto the quantum dot. But the problem is it cannot go out because all of these states in the drain are occupied. So it can go on, but it cannot go off. And so the first electron would go onto the quantum dot if we just made the connection, but then it would be trapped there and the current will be blocked. Current will stop. And of course, the higher level, the n level, is too high in energy. There are no electrons available to occupy this level and to then later get off of it. And then, of course, if you can imagine that now with a gate, we can move this ladder around because of this term here, which we're very lucky, we can move the chemical potential with a gate. And what that looks like, because it's linear, literally, I change the gate and the ladder of mu levels in the middle, mu n plus 1, mu n minus 1, they all just slide up and down. They slide up and down. And so we can slide one of the levels, like in this case, mu n plus 1, we can slide it into the window where, and we can also raise the source as well, or we can keep it there, but we can slide it in resonance or just inside the window between source and drain. And then, of course, you can see that we can have an electron here that will hop down and then hop down again, and that enables current. And so if we plot current versus voltage, we might expect something like this. And if we add more and more levels, we can expect jumps in current. Every time we add another level, it's like adding another channel. For instance, if there's only one level between source and drain, there will be one electron hopping at a time. But if there are two levels, there'll be two electrons hopping at a time. And so current will increase in a stepwise fashion. So you can see we have the control knobs as source drain difference, source drain bias, it is called, and a gate potential. So we can plot what happens in the space of source drain voltage and gate voltage. And what happens there is that if source drain voltage is 0, we are in the resonance situation like this, source drain 0. There will only be current when one of the levels is aligned with source and drain. So three things have to coincide, source, drain, and the level. And this is captured by these spots. But if we increase source drain voltage, then there becomes a window available over which current will flow. And so it expands into these triangular regions. And the triangular regions meet here, but then inside these regions, current is 0. And this is called a Coulomb diamond because it looks like a diamond. In English, this is diamond. You can also call it a rhombus. So this Coulomb diamond is where current is 0, and it's a very useful thing to study because just from the size of the diamond, for instance, from this height, you can extract the energy. And here it is marked as just a charging energy, E squared over c, but it could also include the quantum energy, the orbital energy as well. So then if you know the capacitance, how your gate couples to your dot, you can also from the slope extract the same information from this spacing with the coefficient alpha, which is a lever arm. And also you can just extract the capacitance from the Coulomb diamond. So it gives you a lot of useful information, even the basics of it. But of course, people have studied very fine nuances of these data, and so you can dig pretty deep into Coulomb diamond data. But here is one of the perhaps more striking plots of Coulomb diamonds. So let me guide you through it. First of all, this blue color, this solid blue color, is zero current or zero conductance, zero dI/dV. So that's called differential conductance. And you can see the zero current regions form diamond shapes very distinctly, these diamond shapes. And then these bright colors, white, red, and some of these bluish colors, that's finite current. And you can see there's lines that meet to form the diamond. And you can also see how rich it all is, how very diverse the structure of these dots is. And so all of these things correspond to something. For instance, excited states in the quantum dot, not the lowest energy states, but higher energy states where one of the electrons is not in the lowest available energy level, but in a higher level. Some of the vibrational states and some of the many other interesting things. Now, another interesting thing is that you can see there is a small diamond, large diamond, small, 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 large, small, 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 large. So that's also very interesting because this means that some of the energy levels, some of the quantum levels in this dot can hold more than 2 electrons. So this is not generally possible due to Pauli principle for fermions, but it is possible when there are degeneracies. So for instance, I told you about the one-dimensional box, and then the solutions for it are actually here with these numbers n for energies. But the quantum dot is actually a three-dimensional box, so there's x, y, and z, and you have to solve Schrodinger equation for each axis. And to keep it simple, you basically just solve the same equation 3 times and add up the solutions. The equation falls apart into 3 parts. But that means we have the 3 quantum numbers. Out of these numbers, we can create the same number E in multiple ways. For instance, 1, 0, 0, 0, 1, 0, 0, 0, 1 would correspond to the same energy. And what that means is that there are actually different quantum levels correspond to the same energy. But the source and drain don't know it. So they keep providing the same energy, and there is still the same electrons can go in. And that's why there is a pattern of small and large diamonds, which means that when you go from one small to the next one, you have to always pay charging energy for each electron, because each electron you have to pay E squared over C, no matter what. But then every so many, like the second one, then the fourth one, then the sixth one, you have to pay also the quantum energy. And so you can build a sort of a periodic table of artificial atoms, which is what they did. This is work from Delft University, where I did my postdoc, and from Japan. They made very symmetric, in this case, circular pillars, where all these symmetries are preserved, and really energy along X and Y remains the same. And so in this case, there is no Z. Z is just fixed, but in X and Y, you can add electrons and you can make these artificial orbitals, of course, in contrast with single atoms, where these energy scales are volts, electron volts. Here, energy scales are milli-electron volts, 1,000 times smaller. And that's because each of these dots is made of thousands and thousands of atoms. And the size is much larger than the size of atoms. But these are kind of artificial atoms. Okay, so another thing that we can observe if we apply magnetic field, and this is getting closer to spin qubits, is energy splitting for electrons with spin up and spin down. We can start to see it in the data. So these bright red regions are Coulomb diamonds. In this case, this is really 0 electrons, and this is really 1 electron on the quantum dot. And as a function of magnetic field, as we increase the field, we see extra lines appearing. So these would be the states for spin down and spin up electrons. But they correspond to the same Coulomb diamond, because we have to pay the charging energy to put that electron on. And then the electron that happens to be on the dot is either spin up or spin down. And statistically, it will be the one with lower energy. So for this material, it would be the spin up would have the lower energy due to negative gyromagnetic ratio. And so the first electron will be spin up. So if I put another one, it will probably be spin down. But if I give enough energy, I will see some tunneling and some hopping around between spin up and spin down levels of 1 electron, of single electron. So without adding a second electron on the dot, I will see the energy structure of the quantum levels with 1 electron. So this is called excited state spectroscopy. So spin up and spin down states can be used as a basis for a spin quantum bit. What I also want to highlight is that people have studied, and this is also very useful in quantum bits and quantum technology, multiple quantum dots. So in this case, I told you that the gate can be used to change the energy of the electron on the quantum dot. But in this case, gates are also used to define the quantum dots. So electrons here live 100 nanometers underneath the surface of this material. The gray, the dark gray here is a semiconductor gallium arsenide, and the conducting layer is buried underneath the surface. And on the surface, there are these metallic electrodes that can have very elaborate shapes, but you can recognize what's common between them. There is kind of one opening here and one opening here. And all of these metals are biased to negative voltage, so they push electrons out. They push electrons underneath of the gold shapes out, and they squeeze them into these little volumes and also outside into these big areas. And so if you adjust all of these voltages careful enough, you will have 1 electron here and 1 electron here. Then you can observe tunneling between them, coupling between them. You can study how they form spin singlet states where the spins are oriented opposite, or spin triplet states where spins are oriented in the same direction. And this is all used in quantum information. So just in case you need a refresher on this, this would be analogous to a double well potential, which is also a foundation for a covalent bond in chemistry, if you encountered that in chemistry. So a wave function in a single well would be something like this. And now here I draw little tails underneath the potentials because they're not infinite, they're finite. And this is a case of a hydrogen atom, because this is the energy of 13 electron volts. And this is a hydrogen molecule where the two of these wells, the two hydrogen atoms, are very close together, and there is a strong overlap between these wave functions. And then we can add them up like this. We can subtract one from the other, or we can add them two together. So there is a HOMO and LUMO, or well, two hybridized wave functions that are possible out of these bell-shaped wave functions. So this is I'll used a lot for spin qubits. I'm going to skip this part very briefly, but just to say that the same electrostatics with chemical potentials, but now with two numbers, N1 and N2, can be written down where we calculate the chemical potential of this configuration by subtracting the electrostatic and quantum, if needed, energy for N1 and 2 and N1 minus 1 and 2. For adding one electron to one of the dots. So this is a more complicated model because it also has a mutual capacitance between the two dots, in addition to capacitances to the gates and to the source and the drain. So there is more parameters here, but the idea, the physics is the same, that it allows you to calculate the energies of the different configurations, but now you have to use two numbers. And then there is also the kind of the two-dimensional version of the Coulomb blockade pattern, where as a function of one gate that controls one dot, we have these Coulomb peaks where current flows and then stops and flows and stops. And as a function of the other gate, we have the same. And together, they form not a grid, but a honeycomb pattern, hexagonal pattern. That's because of the mutual capacitance. So these are called honeycomb lattice of Coulomb peaks. And you can even go to triple dots, which has been used a little bit in quantum computing. Well, now they make even more dots, but they think of them as combinations of double dots usually. But in this case, they really did go and make a triple dot. It's a very complicated structure of gate electrodes. And to think about Coulomb blockade in a triple dot, you have to think in three-dimensional space. So these will be the analogous Coulomb stability diagram honeycomb patterns in 3 dimensions with dot 1, dot 2, and dot 3 on the vertical axis. So I know I'm out of time, but I wanted to just mention how it's used for spin qubits. It turns out that spin qubits are better than using charge in the dot, because you could think about, for instance, with two dots, charge on the left and charge on the right, as the states 0 and 1 of a qubit. But that happens to be a very bad idea, because charges are very sensitive to environment, because many things in our environment produce electric fields, like all the things listed here, including your cell phones, produce very strong electric fields, and that leads to the decoherence and very short lifetime of quantum information stored in charge. At least in a basic version of it, because ironically, the transmon qubit, the best qubit out there, a superconducting qubit, is essentially a charge qubit. But still, spin tends to be a lot weaker coupled to all these environmental perturbations. And so even at Intel, where they make these complicated semiconductor circuits, they are wondering if they can deploy their factory where they make processors to build spin quantum dot qubits. And it is going, not very fast, but they are making progress. So this is how experiments look. You also have a lot of this advanced equipment in Kharkiv. This is already pretty old, maybe 10 years old, but this is a dilution refrigerator where you go to millikelvin temperatures at the bottom here. Then you have to connect your sample with some cables and some microwave lines for gigahertz control, because the energy level spacing in qubits is in the gigahertz regime, kind of like your cell phones work in the gigahertz regime, and that makes it very convenient because it's very cheap to use microwave technology to control qubits. So how do we control spin now? I told you we can measure charge by passing current. Spin is a little more, it's much more difficult to see spin directly. You cannot just apply a magnetometer because spin gives a very weak signal. Part of the reason why it can retain quantum coherence for a long time is because it gives a weak signal. So we do spin to charge conversion. So we still want to measure electrical current, but that is spin sensitive to what was the spin of the electron. And the way it works is basically like this. Let me just show you the whole slide in the interest of time. I told you the energy levels for spin up and spin down will be split. So then we load from the lead, from the source lead, randomly spin down or spin up into the quantum dot. Then we try to adjust the potential of the lead right in between the levels so that spin down will be trapped and spin up can escape. And then we look whether there is a signal that we can detect or not. Because when the charge moves, we can detect that very, very well. Even one electron moving, we can detect it. So we can create a selective spin to charge converter this way. Spin up will stay, spin down will leave. And so depending on this, we know that we prepared and read out spin up or spin down on this quantum dot. So this is some of the experimental data. There is this mandatory pulse from changing all the electrostatics, pulsing gates up and down. But then this little blip is what distinguishes the spin down situation, and this will be without the blip, a spin up situation. Okay? So we can even write a script that counts the blips, and we can build a histogram, a plot of the lifetimes of a spin in this quantum dot. And so for this relatively good qubit, the lifetime, which will be the how fast this curve decays, is on the scale of millisecond, 1,000th of a second, which for qubits is pretty good, pretty good. Okay, so you can also you have to also control the qubit, so you should be able to perform the gates that Ilya was talking about just before me. So you have to rotate qubits. In this case, this will be an Adamar gate, just a qubit rotation, and this is done under the influence of microwave signals. So when you apply an oscillating magnetic field to a magnet, you can flip the magnet from up to down. And quantum mechanically, if you supply energy equal to the energy level difference, you can induce transitions from one level to the other. So there is a classical way of thinking about it and a quantum way of thinking about it, but either way, it requires microwave oscillating electric or magnetic fields. And so as a result of it, you can measure current flowing through the quantum dot, and that current will be oscillating. And this is a manifestation of quantum control of spins in this quantum dot by means of microwave signals. So this allows you to, so for instance, if you want a pi pulse, you go to this point, just sort of 50 nanoseconds. You apply microwaves for 50 nanoseconds, and you will rotate your qubit from 0 to 1. And then another 50 nanoseconds, and it's back to 0. Now, since people work with multiple dots, they also thought about more complicated qubits, which are defined on the quantum states of two spins. For example, singlet triplet qubit. I already mentioned triplet is, well, a different parity of the spin arrangement. The easiest one to think about is both spins pointing up versus one pointing up, pointing down. But you can see from here that it's more complicated than this. It's a quantum mechanical superposition of up, down, minus, down, up, and triplet will be up, down, plus, down, up. Now, these are different quantum states of two spins. Again, I only learned it on the first and the third year of university myself. And so these qubits have some advantages compared to single spin qubits because with two electrons of the same spin, you can imagine they cannot be on the same dot. That's the Pauli principle. And so you can distinguish them very easily. If they are opposite spins, they can go together. If they are the same spin, they stay apart, and we detect the difference. And this is called the singlet triplet qubit. So this also works. And you can also preserve rotations of these qubits. And with some clever nuclear magnetic resonance techniques, you can extend the lifetime of these qubits. In this case, this will be the coherent lifetime T2, not the relaxation time T1, and it can reach into tens of microseconds with some what's called dynamical decoupling. Now I'm just spitting terms at you because I'm at the end of my lecture, but I just want to give you a flavor that people have studied nuclear magnetic resonance, which is a foundation for magnetic resonance imaging, for example, the medical technique that is, by the way, discovered at the University of Pittsburgh, where I work. This has been done since 1930s and 1940s. And so there is a very robust set of methods to prolong the lifetime of spins. And so you can use it also to prolong the lifetime of spin qubits. And so as a result of this, already more than 15 years ago, all the building blocks for spin qubits have been demonstrated, including how to initialize them, how to read them out, 1-qubit gates and 2-qubit gates. So this forms a set of what is known as DiVincenzo criteria, which is the initial stage of evaluating if a quantum computing platform can be implemented in flesh, in reality. But some of these times were not so great and not good enough for quantum computing. Some of this is in the nanoseconds, and some of the fidelities were low, and these are kind of stretched numbers anyways. And that's because people used gallium arsenide. This semiconductor was gallium arsenide. It's a very good material, but it has one problem. I told you there is one spin here and one spin here, which is remarkable that we can control this electronic device down to one electron and control where that electron sits. However, every single atom of gallium and every single atom of arsenic also has another spin in its nucleus. It has nuclear spins. And so one of these electron spins is surrounded by about 100,000 nuclear spins. And so the real picture is that there is two spins that we control and another million spins that we don't control. And those spins are flipping around and coupling to our spin and messing with it. Fortunately, the coupling is weak, but unfortunately, there are really a lot of them. And so this became a very fundamental problem that prevented these metrics from improving. And these very clever techniques like spin echo and dynamical decoupling were actually used to go around the problem of nuclear spins, but it created a large overhead on the technology of this. And so people switched to silicon. They started making similar devices. In this case, they implant individual atom with a spin into a silicon matrix. And in this case, they build really a similar structure like what I showed you, and you won't be able to tell the difference from this picture, but this is now implemented in this gray layer is silicon. And the difference between gallium arsenide and silicon is that gallium and arsenic are in the column 3 and 5 of the periodic table. And all atoms in that columns have nuclear spins, and all the isotopes also have nuclear spins. But silicon is in the 4th group of the Mendeleev periodic table. And so silicon has many isotopes without nuclear spin. And this is why now companies like Intel are also excited about this, because they have built $10 billion factories to work with silicon. And it happens to be a better material also for spin qubits. So there is now a lot of efforts building them out of silicon. So this is my lecture. I know I went over time, and I thank you for your attention. And if you have any questions, будь ласка, питайте українською чи англійською, чи як вам зручно. Дуже дякую.
Дякуємо Сергію за чудову лекцію. Тож подякуємо. В мене відразу питання, може також школярам цікаво, що нас тримає від того, щоб робити експерименти з квантовими точками за вищих температур. Тобто це досить низькі температури порівняні з надпровідними кубітами. Чому не можна з квантовими точками трошки вище працювати?
Можна трошки вище, да. Можна, в принципі, піти на 4 Кельвіна, що вже температура рідкого гелію, так? Тобто не потрібен такий dilution refrigerator, а можна просто залити гелію чи використовувати звичайний компресор. Це дешевше і це зручніше. Через те, що треба дивитися, які енергії тут. От дивіться, будь ласка, які енергії спінів. Міліелектронвольт. Я вам казав, що 100 мікровольт – це 1 Кельвін. Тобто 10 Кельвінів – це міліелектронвольт. Тобто, в принципі, ми можемо собі оперувати на температурах таких, як 3 Кельвіна, 4 Кельвіна, 2 Кельвіна. І у нас буде достатньо енергії, щоб бачити спектр цих квантових точок.
Так, у нас є питання від Сергія Шевченка.
Сергій, дякую за цікаву лекцію. Ви порівнювали, you've compared single and double or multiple quantum dots. You've said about both. Can you compare now them? Can you say which ones, say, single and double quantum dots are better for creating charge and spin qubits? See, by saying about multiple quantum dots, I mean single electron ones.
Mm-hmm. Yes, thank you for the question. Ну, всі використовують двойні точки, double dots. Чому так? Тому що what's this? Okay, I will speak English, I think, sorry. These, I didn't have much time to explain, but these states, singlet and triplet, they allow for full electrical control of the qubit. So, for example, to rotate one spin from up to down, normally you need oscillating magnetic field. This is how we do nuclear magnetic resonance, electron spin resonance. This is how MRI works, the magnetic resonance imaging machine. We have to apply large oscillating magnetic field to flip spins in your brain or in your body. And creating oscillating magnetic fields is difficult because you need to run a coil. Maybe there is a picture. No, there is no picture. Sorry. You need to run a coil on top of quantum dot, another coil, and pass a large current through it, which creates also heating and phonons and all kinds of bad things. And so it is better, and you know also your smartphone, your computer, it's all electrical control. Everything is electric. So we know very well how to supply electric fields to small circuits. And this is what we can do here, because the coupling of these two spins is controlled by electrostatic gates. So we can bring them closer and they will spin faster. We will bring them farther and then will spin slower between these two states. So if we eliminate the problem of nuclear spins, then this becomes a better qubit. And then charge coherence times are less than 1 nanoseconds in semiconductors. Of course, in a transmon qubit, we know it can be milliseconds. Yeah. Олександр, є питання. Я бачу в Zoom.
Так. Дякую за доповідь. У мене теж є питання. Коли ви розповідали про подвійні квантові точки, то я бачив таку схему і вже не один раз, що система ефективно моделюється як такі острівки, які поєднуються елементами, які складаються з ємності і опору. І мені цікаво, я не можу довго зрозуміти, чому саме важливо ось наявність цього опору також, як це там впливає на процедуру квантування, якщо ми, наприклад, хочемо або цікавимось динамікою квантових точок, хочемо їх розглядати як кубіти.
Це про ці питання про те, що я показував тут, оці елементи.
Ну, наприклад, тут, але, здається, трохи далі в презентації це теж було, можете.
Ну, я про це не багато казав, но...
Так, ви не казали, це просто...
Є такий режим, в якому цей елемент, у нього its value is higher than 1 quantum of resistance. So quantum of resistance is 6 kilo ohms or 12 kilo ohms, 12,000 ohms. And if you have resistance higher than this, then you are in a tunneling regime. It means that electrons don't flow through, but they have to hop, tunnel. And so to see some of these discrete quantum effects, you need the electrons to tunnel on and off. And where the number 12 kilo ohm comes from, it's E squared divided by the Planck's constant. Why is it significant? Because if you calculate the resistance of one chain of metallic atoms, where you hop from one atom to the other, if two objects are connected from one atom of metal, resistance will be 12 kilo ohms, 12,000 ohms. So I'm not sure if it answers your question, but basically below certain resistance, you are sort of free-flowing through this. There will still be quantum effects, but there will be no localization. Electron will not, you cannot think of it as stuck on the quantum dot. It will be more like a wave traveling through. And above certain resistance, it will be localized.
Okay, but can we use the capacitance instead of resistance in the case it's also about tunneling?
Well,
or is it necessary to consider this as resistance?
With capacitance, I suppose we can do it if it's an AC circuit, right? In a low frequency, zero DC direct circuit regime, there will be no transfer of charges. So in this case, charge has nowhere to come from, right? Imagine there is only this capacitor and these resistors are not there. And I keep increasing the gate voltage. Where would the electrons come to the silent from? I will just be raising the electrostatic energy, but they will not be able to come. So we need the tunneling, and tunneling happens in a zero frequency regime already in DC, and it is modeled by a resistor.
So resistance on the quantum dots schemes are depicted just to make sure that we have correct physical understanding on how the Cooper pairs or electron tunnel on the dot to the dot.
Right. Well, if it's Cooper pairs, it's a little different. So this we did not talk here about at all. The resistance in the Josephson junction, that's it's a different topic. Maybe we shouldn't start on it.
Okay.
No.
Okay, thank you.
Сергію, в мене таке буде до тебе просте дуже питання. Дякую. Ну, перш за все, дякую, дуже цікава доповідь була. Я так розумію, і нашим молодим колегам також. Але я думаю, що для школярів та студентів таке просте питання, відповідь на таке просте питання, яке я задам, буде дуже цікаво. Особливо для тих, хто вперше почув, що таке квантові доти. Ну, питання таке, де ще можуть бути практично використані квантові доти, окрім як компонентів для кубітів в квантових комп'ютерах? Дякую.
Ну, дякую, Андрію, за питання. Цікаве питання. Ну, що я можу казати, що, по-перше, ті транзистори, які існують в чіпах, того ж, наприклад, Intel чи Apple, Samsung, вони вже такі маленькі, що там кількість електронів у одному транзисторі чи dopant sites там вже, не знаю, десятки. І тобто ці об'єкти, вони вже у квантовому режимі насправді існують. І розуміння квантових ефектів вже починає мати вплив на девайси, які ми використовуємо в нашому житті. Ну, майже. Ну, треба, коли їх дизайн робиться, вже рахувати і charging effects, і quantum effects. Тобто це вже має якийсь вплив на технологію. Ну, там вже 7 нанометрів пішла технологія на один транзистор. Завдяки ASML. По-друге, ну, щодо таких квантових точок, як я показував вам, таких транспорт, я не знаю, чи там є такі прям технологічні у них корисні приклади, але ті, які хіміки використовують, вони використовуються там для dye lasers і прочого. Такі різнокольорові пробірки, якщо ви Google напишете Quantum Dots, ви побачите, що вони вже в технологіях використовуються, в оптиці. Ну, ще одно, якщо вам потрібні фотони, які запутані, entangled photons, чи single photon source, то також в оптиці можна використовувати квантові точки, тобто це як quantum emitter. Або які ви можете контролювати електронікою. Не як газ, квантовий газ, а як такий квантовий девайс. І single photon laser, такий. Ну, приблизно так.
Ага, дякую, Сергію. Я там бачу ще питання онлайн є. Будь ласка, задавайте.
Добрий день, дякую за лекцію ще раз. Було дуже цікаво дізнатися про це, я вперше про них чула. У мене виникло питання щодо одних з останніх слайдів. Я його в чаті написала ще англійською. Від чого залежить, що ми можемо контролювати тільки 2 дотса, і чому більше не можемо?
Ну, ми можемо. Дякую за питання. Так. Ну, ось, наприклад, тут 3, такий приклад, де 3. Тут дві речі можна казати. Перше, що для одного кубіту ми використовуємо дві цих точки. Тобто, якщо нам потрібно, я не знаю, 10 кубітів, нам треба 20 точок. І зараз такий state of the art це, я не знаю, скільки, 4 чи 6 кубітів. Тобто це буде 12 точок. Тобто це вже існує. Є вже такі статті, де вони працюють з багатьом точками. А чому для одного кубіту ми не хочемо використовувати більше точок? Ну, просто подивіться, яка складна структура, щоб було 3 точки, які дуже близько, щоб був танелінг між електронами. Тобто треба 1, 2, 3, 4, 5, 6, 7, 8 електродів, і їх форма дуже важлива. Тобто треба, щоб були такі товсті, тонкі. Тобто це дуже складно. І вже 2 точки це вже складно, а 3 і більше це буде складніше. Тобто, коли вони роблять девайси там, де 4 кубіти, то між ними coupling capacitance. Да? Тобто вони далеко, у них відстань багатий, великий.
Дякую за відповідь.
Дякую.
Дякуємо. Ну, наразі питань ми не бачимо, тож дякуємо ще раз Сергію за таку доповідь, за огляд високотехнологічних надбань, що наразі нагадують навіть якесь мистецтво на цьому слайді. Дякуємо.
Дякую.
Тож на цьому завершуємо 3-й день школи. Дякуємо всім доповідачам і сподіваємось побачитись завтра на заключному дні.